Welcome to Unit 3, and this is Session 2. And in this session, we are looking at the rate of reaction. By the end of the session, you should be able to drive the general rate law, determine the rate law from a given data, and determine the reaction order of a rate equation. When we talk about rate of reaction, the rate of reaction is defined as the increase in concentration of product per unit time or as the decrease in concentration of reactant per unit time. One example of a reaction that has been studied in detail is the thermal decomposition of gaseous dinitrogen pentoxide to give the brown gas nitrogen dioxide and molecular oxygen, which is represented by the equation below. Now, taking this data, this is an experiment that was conducted for the above equation or experiment. So these are the times, these are the concentrations. So when we are looking at rate, we are looking at the time it takes for the reactant to decrease in concentration per unit time. So when we are writing the rate law expression, we write it with respect to what time. Now realize that when we want to write the rate law expression relating this the nitrogen pentoxide and then nitrogen dioxide and then oxygen, then because this is a reactant, we assign a negative sign to it because the concentrations are decreasing. However, the concentrations of the nitrogen oxide and then the oxide or the oxygen gas increases, their concentrations increases, and for that matter, a positive sign is usually assigned to them. So we write it as change in N2O5 divided by the change in time. However, remember I said we always assign a negative sign to it because the concentration of the reactants are decreasing. So the rate expression is given by this. Now, if you want to, however, when you write the balance equation, because of the stoichiometric coefficient, then we need to also make use of them. So when we are writing the rate expression, we factor in the stoichiometric coefficient. So with respect to N2O5, then we're going to have negative 1 over 2, then the change in N2O5 divided by change in time, which will give us 1 over 4, and in that order. Now, the rate law and the reaction order. Considering the general equation, reaction A plus B going to give us a product where A and B are the reactants and then the small a and small b are the stoichiometric coefficient in the balance equation. The dependence of the reaction rates on the concentration of each reactant is given by an equation called the rate law. The rate law is generally in the form as rate is equal to change in concentration of A divided by time, which will give us K is equal to concentration of A to the power n, then the concentration of B to the power m, where our K is what we call the rate constant. The rate constant. And remember, I said earlier on that the units of K vary depending on the order of the reaction. Now, for rate law, anytime the rate law is a zero order, usually R is equal to K. R is equal to K, and the unit remains the same. Okay, the unit, basically there is no unit for K, but if you are to find K, then you just get a raw value. When the rate law is a first order reaction, this is a representation. R is equal to K concentration of A to the power 1, but as you know, we usually don't write the 1 over there. Okay, so for a first order reaction, the unit of K is always per second. For a second order reaction, the unit of K is always per second, per molar per second. And that of a third order, which we might not be treating in this particular chapter, is always per molar squared per second. Per molar squared per second. So take note of the unit of first order and second order, and as well as note that for zero order, the unit of K are not indicative, or there is no unit for K for zero order reaction.